do for that is to load in your own memory the image of what you think is running beside you. Then you wait a bit, because KSM deduplication process takes time. And then you write to some of those pages, and then you measure the time it takes. So if the time it takes to do the write is much longer than the normal write inside your virtual machine, it means that you got KSM involved all the way down from the host. It gets the page deduplication for you, and it means that you have a match. You basically notify what is running beside you. All right, coming back to that picture again. I realized there was another problem with my design. Basically, there is no synchronization primitive across processes running a different VM. Remember when I was running directly on the host, server was signaling a mutex, the client was signaling a mutex, server was waking up and doing the decoding. But here there is no such thing. Well, in reality there is things to do that. For example, on Linux there is, at KVM there is IBSHM, where you can basically from one VM to another signal a semaphore and so on, but that stuff is not enabled in production. We need something to replace the mutex. Why? Well, because we want the server to run right after the client, so that he's going to pick up the signal, right? Remember what happened if we wait too long? All the data is gone, so we have to be fast. So then I ran a couple of options. I did not really know how to attack this thing. So one of the options I had was basically, I'm just going to forget all about that synchronization aspect and kind of hope for the best. With error correction, ECC, we can achieve some data transmission. You know, obviously there is space between the client and the server, and it's totally random. So this is going to give us very low bit rates, obviously, but the CPU consumption is low. And now that's kind of cool because we need to be, we don't want to burn CPU because everybody's going to detect us, right? So another option. It's basically, I set it up such that there is a busy loop on each side, and the client is set up to run a bit faster than the server. So at some point in time, there will be an overlap. And at that point, the server will pick up the signal and the transmission will happen. So this is giving an okay bit rate, but the problem with that one is that the CPU consumption is very high. And this is no good for us because we want to remain undetected. Hopefully, well, we would like to be less than 1% CPU usage, sorry. Option number 3. So this is basically my phase log loop implementation that I was talking at the beginning. Let's define a common period on the server and the client, and let's have the client and the server log into phase. How I did that? Well, at the beginning of each period, I have the server that is sending out a sync pattern. This sync pattern is very similar to what you found in those analog TV for the vertical sync. That's the kind of the same concept. And then you have the client that is running a sweep scan over that period and tries to detect that sync pattern. Once it detects it, it basically locks on it. So obviously, once the sync is detected, the client is just shifting back the phase, and now we are ready for transmission. But there is a tricky problem for that to work. We need a monotonic pulse. We can, in theory, tolerate some jitter, but not too much, because in the end there is lots of noise and the data evaporates out of the cache very quickly. So in practice, all that stuff looks fine, but in theory, all that stuff looks fine, but in practice, it's a bit more tricky. How can we achieve a monotonic pulse? First thing comes into mind is to use timer. Well, timers are good because anyway we need to sleep in order to avoid detection. But with timers there is a big problem. So this is a graph that represents the latency in microsecond, that is the latency distribution in microseconds of a timer that is running in a VM. This is a log scale. So we see that from that graph, there is lots of jitter. I mean, it can range from all the way down to 20 microseconds, all the way up to almost 200 microseconds. And now if you factor in the original design, this timer, this jitter from the timer is going to come from both VM at the same time because they have the same type of distribution. So there is just too much jitter for that to work. The data will not persist and transmission will not happen for sure. Okay, so the idea I had was to basically compensate this timer in software to some value above the maximum jitter, so that in theory this should give us a nice monotonic signal. Well, here we need to be a bit careful because this compensation thing is going to be subject to noise. In other words, what I'm trying to say here is more time you're trying to compensate something, more noise you end up accumulating from the underlying stuff that is running behind you, right? And the other thing that needs to be that we need to be careful with is this compensation is burning CPU. But on that aspect, it's not too bad because all we have to do is to stretch the timer period to some higher number, and we will still stay under 1% CPU usage. All right, it's a tricky problem, but I believe at the end I got it right. The compensation thing I'm using is basically a calibrated software loop that is kept in check with the TSC at every single point in time. And this is the result I got. So my machine is a 2.4 gig machine, and when I'm running idle, this graph represents the jitter that I have on my compensated timer, and it's in cycle. So I have roughly 50 cycles of jitter on my timer. It corresponds to 20 nanoseconds. Even on a loaded system, I've got roughly 300 cycles. It's 120 nanoseconds. It's pretty fast, pretty accurate, sorry. If you compare that with the original timer, I mean, there is obviously no comparison here. Even if we put the latency back into perspective with the original graph, the jitter doesn't even show up on that scale because the original timer was a microsecond scale, and now I'm working in nanosecond scale. And as you may already understood, this synchronization aspect is the key of this design. Because it basically enables the communication to happen with very low noise, because it's very, very precise across the two processes running, and at the same time it consumes low CPU. Okay, let's recap what we have so far. So we have an encoding and a decoding scheme that is based on memory access time. Slow is a 1, fast is a 0. We managed to get rid of the output prefetcher without disabling it by the BIOS, because we just randomized the cache line access at the page level and so on. We also found cache lines that are shared across VMs, and that is thanks to KSM, by the way. And we managed to design a phase lock loop that basically gives a very high precision across two processes running in different VM. Time for a demo now. Okay, so I basically, with that technique, I basically repeated the original experiment, which consists of sending that DEF CON logo from one VM to another. We can see that this technique is offering pretty high quality and kind of low noise communication channel, at least if you compare that with the original pipeline contention example I showed you at the very beginning, right? So there is no error correction that is running on the transmission channel. There is no retransmission, nothing. But as you can see, if you look carefully, you'll see that in the picture there is a couple of bits that are flipped here and there, and that's expected, right? The channel is kind of noisy a bit. All right, then in that experiment, again, it's a recording, I repeated that exact same streaming experiment with my noise generator running on and off in the background. The first thing I want to mention, and that's kind of cool, is that when the transmitter is not running, the receiver is picking up the noise from whatever is running on the operating system. So to me, this could potentially be used to fingerprint the operating system that is running underneath. Also, with this recording here, same stuff than the previous one, I have the MP4 encoding software that is running on the same machine and so on. So on its own, this thing is generating quite a bit of noise. But still, you will see the effect when, let's say, I move a window around, for example. And of course, you will also see the effect of when I compile the Linux kernel. You will see the noise going on and off and so on. One last thing, I may have mentioned it before, there is no compression.